Okay, I think this is true. If it's not, we can finish now.
Yes, so we can start. Yes. Yes. So this one is okay, right?
Yes. So
this is a start of solution of problem one. So commutant of n classes is given by the direct sum.
okay, so.
That's definitely
Okay. Okay.
The sum is not direct.
yeah, but
Because
Some of them are zero.
simple roots, maybe not.
Well, it's just. Well, we can write it in simple roots.
If you replace r plus with y, it is direct sum, right?
Yeah, the next step I want to change
no,
it.
I don't believe it's there. Wait, what?
No?
So as it's written, it's not direct, right?
But do we actually care if it's direct or?
No.
No.
There's written direct.
Well, how to read not direct? Just a
There
sum.
is a technical issue, I guess.
No. So if you replace this with y, then it's direct, right?
Yeah.
Okay. If r plus, not sure.
Yeah, but then the inclusion.
Well,
Won't be
obviously
true.
you can have two different compositions of sum of simple roots that give the same root, right? Like
No.
Because it's a
Simple
basis.
roots is basis.
Yes.
no, I mean not this, but in case you have the r plus
Yeah,
there,
there.
you can just like
Yes,
consider.
r plus, yes, you can.
Yeah, but if you
Well, I think not in
if you
two-dimensional
write
case,
p,
but
it will be not true. It's just don't be true because it's not lies in sum of only two alpha I
I
plus
don't think
alpha
we
g.
care if it's actually direct or not, because I don't think proof actually.
You mean
works.
you can't write it here k
No,
if it's p?
There, everything
But yeah, I
Right.
understand.
between, but the direction. Of
Well,
this
okay.
direction.
Let's think let's think that it's not direct sum.
Okay, so direct sum we don't need.
Okay. So now every positive root has a maximal length of decomposition into simple roots.
Every positive root has.
Well, because we have because we,
what
well, I mean every alpha from R plus has decomposition into simple roots.
yes.
And we can choose with the maximal number of these слагаемых.
These terms.
Yeah.
But,
Well, it's
what
because
do you mean maximal number of these terms? Maybe we have two. So we can have two roots with maximal terms, right? So you also can
No,
have coefficients here.
Yeah.
Right?
Yeah, but I mean that the sum of coefficients is limited for every single.
Yes.
So like we have for every alpha we have k where I mean this term wouldn't be for this alpha for some k.
So you mean if I have alpha is sum and I alpha I, right? Then you just what is called define what is called height, right? Which is sum
Yeah.
over coefficients.
Okay, yeah.
And you would like to choose alpha of maximum height. Is that what you're doing?
No, I want to say that for every alpha, this height is like finite, not
Yeah, it is finite.
so we have finite numbers of roots.
Yes.
So there exists a k when this thing is 0.
Well, I suppose when k is just equal to the cardinality of r, it's always it should be 0.
Well, you can change. You can choose with the maximum height, and now take the
I'm sorry, what should be 0?
these things. Like we choose with maximum height. Okay, alpha is with maximum height. Now we
Yes.
take the
Yes,
Wait,
okay.
with that? Yeah. So this thing is in 0. So it's nilpotent.
Okay.
And same with n minus, I think.
Yeah, same with n minus.
Yeah, and yeah, I forgot the notation of height. Okay.
Yeah, so here you need to take not the height, but maybe
Height plus 1.
height
Yeah,
plus
maybe
one.
yeah. And this we can get from our relationships.
From root decomposition as well, right?
Yeah.
Or
Yeah, well, like we know that this is the basis, this generates.
right.
And if we take something generated by two different so this is just yeah, and this is in n plus and this is in n plus. So that's all in n plus. Okay, and as it's nilpotent, then this is solvable. Okay, I think that's it.
Yeah, ask, like, you said that this contained in n plus, yeah?
Yeah, because this thing is contained, so this is contained.
And like any
Yeah, you would like to
subalgebra of nilpotent algebra is nilpotent.
every subalgebra of nilpotent
Yes,
algebra.
of course.
It is.
Okay.
But actually, it is equality, right? You can show. I think you can show.
Yeah, I suppose
It's
it's equality.
equality, but we don't need equality.
You don't.
So in order to avoid possible wrong statements.
Well, we
use
can
it-
prove that it's solvable if it's contained in n plus.
Yeah.
Yes.
Very good. So number 2 then is we have Kuznetsov Yuri here, but he's not here. Like how?
Well, what?
Maybe he has a representative here. I don't know.
Wait, can I-
Oh, I suppose I just missed.
Ah,
Sorry. Maybe.
We had
Sorry.
like a discussion with him that I asked him to show up at least at some seminars.
Sorry.
But
I just. Yeah.
so I thought that maybe the day had come, but no.
It was just an illusion.
Okay, Mark, maybe you can. So
Yeah, probably.
yeah. Okay. So okay, I'm going in this order now.
Fancy.
Nobody's. No. There's one. Two person. Two people. So.
Then, which one should I?
I think this one. I think they both work.
So, okay, I wanted to construct an morphism, then prove that this morphism is correctly defined, then prove that this is surjective, and I suppose we showed that dimension of G of R is equal something like this statement. The dimension of G of R is equal to this. So, okay.
This uses Serre's theorem.
Yeah? Well, then I actually don't have a proof. So, okay, I just use it. And how it uses? So, like, how we prove this statement?
So Serre's theorem is saying that your semi-simple algebra. So G of R is a semi-simple algebra with abstract root system R. That means that you can compute dimension like that because it has all one-dimensional root subspaces and Cartan subalgebra. One-dimensional root subspaces. Each dimension gives you the size of R, and Cartan gives you the size
I
of
understand. So, yeah, actually.
Then
Sorry. Sorry for that.
okay.
Can you prove the statement using direct traces?
Not today.
I think it's possible.
It is possible.
Which one? This one? Yeah.
So, firstly, let us write Serre relations for I and diagram. With the following form. Firstly, we have classical relations like this.
Я замечательно решила если поставить.
Нет, я думаю, это просто на это не поставить. Ну, куда мы скипнули? На самом деле.
As the action of H elements on these elements is given by the rule. And similarly for F. No, this follow from the fact that Cartan matrix have the following form. And we have at the end the following relations. For other indexes we have the following. No, and similarly for of type F.
Yes. Okay.
So the idea, we need, as we have shown before, we need to show some. We need to define dimension of this algebra.
Yes.
The idea is for.
Homomorphism we know, right? We can.
Yeah. Firstly, we know that we have a well-defined morphism like this, which send generators by the rule like this.
Вот, собственно, маркетинг. Потому что высоверенность соотношение не получается.
And furthermore, this morphism is on to science images of generators are generators in this algebra also. So the problem is, suppose we have here some another non-trivial relations, hence we need to show, to complete the proof that this is an isomorphism, we need to show inequality. So the idea is to show, to give some basis of this algebra. So firstly, note that relations of type 1, 2, and 3 ensure us that the following algebra has a decomposition as a vector space. Where by this I mean that it is a B subalgebra spanned by E-type elements and related for F. And furthermore,
So
the
why
relations.
YGE is subalgebra? Is it?
No, we take all possible commutators on E.
Yes.
And we
Yes,
obtain,
yes.
in other words, we obtain a Lie algebra on E with the following relations. And similarly to F, where don't, in some sense, affect on each other because of first relations of this type.
Okay.
And furthermore, both of these algebras are isomorphic. Hence, we have four.
Sorry, how did we again obtain the sum is direct? Versus
No, just
how
as
is-
vector spaces.
Can you again explain what is GE?
No, it is a Lie algebra obtained from generated
by
by
EIs.
E elements and relations of four type.
Relations, okay.
Yeah, we don't have some.
So GE
Twisting
subalgebra is
between-
in GAM generated by EIs.
Yes, okay.
And
And similarly for GM.
Yes, so
Then the question is why it's equal to the whole GE.
yeah, that's my question too. Why is it equal to the whole GAM?
Yes.
Why is not some sub
we need to check that there is no.
Because of suppose we obtain some Lie algebra from E, and then we act by elements of type F on this space. Yeah, suppose. The relations on where commutators verify us that we don't get something new. So
Why?
elements will
Why?
belong to this direct sum.
No, if we take EE and commute it with FE, we take
We
HE.
take H.
Yeah,
Oh,
so
but
we will.
No, I mean that what okay, we have this as a subspace, yeah?
Okay.
So only what we need to check that this space is invariant under joint actions of generators, yeah? If we will check it,
Yeah.
we get.
Well,
So
that's-
no,
Why-
the relations
why?
above explain
Why
that-
is it so?
Oh,
So
wait,
you say
can
that
I-
there is no ideal?
Can can I ask? So, okay, I agree that if you take just is and just
Yeah.
commute it with generators, there you indeed get something from the spec. But in fact, you have elements in this GE that are not EIs, right? They have some like long commutators with EI, EJ, and so on. And when you take
Yeah,
a joint
yeah, yeah,
action with
I-
H, it's kind of non-trivial that what you get is you exactly get it like from there. You need to check it somehow, because it's not trivial at all. Like for just simple EIs, it's true, yeah, it's trivial. But what about like big commutators? I think it's requires some induction at least by the length of the
No,
commutator.
yeah, maybe induction, something like this. I leave it to the
To the reader to check.
Well, but yeah, that's what I mean by saying that this problem is very technical and very like.
No,
I still think you don't need this, but it is true what's written. You just so what is needed to check right here is that there is no expression like mixed expressions, right?
Yes.
Like H,
yeah,
F,
all mixed.
and so you just need to check that right. If you have something of different sort,
Yeah.
right? You just use these relations, right, to get. So E in and F gives you H, and H with E gives you E. So it's you just. So I guess what you do.
Well, commutator of such type, it's usually like.
So this is
E
just
with
one.
F give us-
This is just some one like this is belongs to. Yeah.
I mean, I think there is
Not
there is
so-
no
not
easy
so
way
obvious.
to check it.
No, not so obvious, right? So something needed to check still, but I don't think that you need this.
Okay, yeah, I just for.
Like this
Okay,
this particular quality, I'm not sure if it's needed for this problem. Okay, but of course,
Well, you need
this is some statement that should be checked, and that I agree. Yes.
You can claim that.
Okay, we can make it. No,
Okay.
we can prove statement without this.
We
So-
have one more comment.
You can claim that.
No,
the
my
sum is
idea
direct.
to.
Denise, wait.
Yes.
Respond.
Can you replace direct sum to simple sum? Because you can't claim that the sum is direct. Maybe some commutators of is equal to h.
But
It isn't obvious.
No, I mean that. Okay, let me write carefully.
Yeah, nothing is obvious.
By J, I mean that any algebra on EE with the following relations.
Is there freely algebra?
no.
The definition of this subalgebra doesn't depend on
Free
H.
with relations, right?
Huh?
Free with relations.
With the
Yeah,
relations.
yeah. Generated by generators and relations. That's all. So my idea to
So we still don't believe in this decomposition, but maybe it's not needed. Okay.
No, I
Well,
my idea to
obviously
show.
I think we-
Okay,
it's
I
crucial.
small
ignore,
solution.
I ignore this statement. Okay, I ignore this statement. We will check it later.
Okay.
Consider just subalgebra spanned by these elements. Yeah. No, with the following generators and relations. I want to show the following inequality. The idea is to present some concrete basis. Yeah. So, no, we want from these elements that they need to correspond some basis of usual Lie algebra. No,
Yes.
matrix Lie
yes.
algebra.
Excellent.
So we define for.
Well, I think you can write it with big ITs or whatsoever. Sorry, your proof does not need this.
No. This no.
I would be very interested to hear, to be honest.
Okay,
But
I shall.
sorry, the idea is that you just need to create something that span GAN.
That's
But then you say okay, I know their image in GLM, in SLM, sorry, and image is a basis. So therefore, it's a basis. That's it.
Why is it?
oh
Why is it true?
oh
I mean, if you have a homomorphism
Yeah.
and you map something that spans your source to a basis, then what you started with is a basis.
well, how do you check that it spans?
Well, just because you know you just check that all expressions that you have are only reduced to you are only left using this. You are only left with expressions that correspond to the basis.
I'm sorry, your basis is this, right?
Yes.
Okay, well, don't you need to like check what is like HI with this thing, what is FI
Yeah,
with this
okay.
thing?
If you want,
Like, should you really, I think you should check it to be like completely honest. Like to understand that this also lies in the span, right? So it's not an easy check by any means, that's what I'm saying.
Yeah, so once you created this, right? So
Even if with this basis, it's obviously a good approach, but it's still hard to do technically, I would say.
okay, if we don't believe in this expression, we can
No,
do the following.
Really?
For G, for this inequality, we define the elements in similar way, but we replace each E by F. And then we check for larger class of elements that were spanning set. So, no, just reduce to case of E to make some
Yeah.
computations.
Yeah, perfectly fine with just only considering only i's. I think it's just still
So
still need to check.
I understand. You're saying that then I should compute this with commutator of this with
With at least
HI
generators.
and say
with all
that it is
generators.
still in here.
Yeah.
And then you need to compute this with
Yeah.
Fi, say.
And I'm saying that this is some induction needed here, and possibly it's needed with the
Yes, I think
how to say it, Jacobi identity and induction.
Yes, I think you're right.
But it is clear on induction. You
Yeah.
rewrite
Yeah.
it and
Well, you need to use Jacobi identity, then I think. Yeah, but
You
as,
need to use
as I'm saying, it's like
that
four different
commutator
inductions.
is
yeah.
you need to use that commutator is differentiation, which is the same as Jacobi identity, right?
Yeah, of course.
Yeah. And then you just apply this by Leibniz rule and use induction.
Well, yeah, another way to say it. Yeah.
For AIJ. Now.
Well, I'm just saying for the
No, by
for
me,
the old
by
book,
I
you need
mean
to like
the linear
check
span.
it all. Yeah, and it's kind of a lot to do.
So this task, it is done in several steps. We consider some special cases, and using relations, we obtain this identity. So, let me just give some sketch. Yeah. For example, for fix some element like this, yeah? Consider K or equal, I don't know, we have by the definition.
Yes. How do you check that there is nothing more than EIJ?
Yeah, so you use this relation. So well, maybe it's a question to Denise, but
Science by the definition, this algebra obtained from all possible commutators, yes? And this set contains origin generators, yeah? And we get some.
Yeah, but I actually doesn't
Okay,
believe that why you can't use something like HA, FJ, EK, and so on, and construct
so now
something
we just reduce
rubbish.
to the case of E. The general case is easily recurved. In the same way, we define elements like this, just replace E with
Yeah.
F, and then for these expressions we check for E, for H, and for F respectively.
I'm sorry, I think the main point here is the commutator of mixed things gives you just single generator. So that's the main instrument that we're using. So actually, if you just
it's a base of induction, I would say.
it's like it's like in the proof of von Kerber-Goffin theorem.
I think it's similar to it.
But I think you just can start with two elements and say, okay, let me consider which ones I can take. So if they are just a flag one, right?
Or they have to be adjacent.
Yes. Otherwise, it is zero. But if they are mixed, right, then I'm back to just generate, right?
Yes.
But then, right, when I add it, I need to add something which is close, like which stays. Right. If I take like 2, 3, 4, 2, 2, and 3, right? Where I mean this is E 2, 3, this is E 3, 4, right? Mutated. Right, and I have like a bunch of them, like 1. Then what I can add is either to here, is either E1, 2, or E4, E or E4,
4, 5.
5. Because otherwise, if it will be like far enough, I just use Jacobi identity here.
Yeah, that's induction.
And this is
This is an
so you just proceed like that. But if you try to make F here or H, right? Again, you just use that your degree drops by 1.
Well, I think the easiest way to proceed is just like because we know that this is an isomorphism, like all the formulas can be just obtained by checking it for SLN, right? And then just proving all these formulas by induction. I think that's the most like.
Yeah, so that's how you create this, right?
Yes.
Then you say, okay, this is linear independent.
Well, we don't need linear independence, obviously. We just need that it's.
Why not? You need to compute dimension of
Yeah, but I only need to inequality, right? Because I have inequality for one side, and I need inequality for the other. And if I just present you these bases, well, you obviously can count how many elements are. I mean, not bases, but the linear generating set.
Yes.
You can compute how many elements in there. You will see that there are exactly n plus 1 square minus 1 elements. And they span, that means the dimension is less or equal than it, and that's what we want. Like, because checking linear independence, I guess, is even harder. You will need to assume some commutators and other stuff.
No, you don't need to check.
No, if we check that it is spanning set, the dimension, by the dimension reason, we guess that it is a base.
Yeah, it's actually, it's trivial, yeah, okay.
No, I just write some sketch. Yeah, for example, for k equal to I minus 1, we get the, by definition, element from this spanning set. For k equal g is similar way. The idea is that when we apply this operator, by some serial relations, it always will commutes with another commutators. Hence, we can replace this operator to our element, and hence we get the for the following case we use the similar idea. something like.
I suppose this case
And
should
it
also.
would be easy.
I suppose this case should say about the k that's between I minus 1 and j. Inside.
No. Last case, it is a direct consequence of these two cases. If you look carefully. Yeah. So.
The consequences are so hard.
No, it's just computational task.
Yeah.
I just
Sure,
do
yeah.
some.
That's I fully agree.
Yeah.
That's a computational task.
And the idea is that we can do the similar for all elements, like we define for F basis elements and for H, and do in similar, but we will have more computations.
Yeah.
So this claim completes the proof.
Yeah, sure.
Thanks.
Or in other way we can use verbal brackets. Obtain this.
I'm afraid to ask how.
I don't know.
It's a lot of computing.
Maybe
No, we need to define some order of monomials.
the main problem was to compute the dimension of this GA and
Yes.
Of course.
Yes.
Grobner basis can compute dimension of algebra given by relations.
Okay. The idea is that for Grobner basis, the idea to prove that relations form Grobner basis for some monomial order. And the form of basis elements ensure us that
The only problem is that here we have commutators, free Lie algebra, but not just algebra.
Yeah.
But we
it
can
is
go-
easily
we can-
applied to Lie case. But we replace
Yeah, how
concatenation of words by where brackets.
Yes. It's not associative though, but it's okay because you have yes Jacobi evidence.
I think we can just go to universal in the algebra.
You can prove
And apply it
diamond
to the-
lemma for Lie algebras and then.
Okay.
Hell yeah.
There is a second part of this problem.
What?
About G. And this is
No, this is
this is
the other
Okay,
technical problem.
Okay, so let's do point 11.3.
Сколько людей сделал?
Два человека.
Неужели есть люди? There are some heroes.
No, this I think it's actually I don't know. You never know, but I think it's better than the.
Yeah, it's definitely better, but after solving problem 2, you kind of blow out. And you don't want to
Okay,
solve.
Nikolai, maybe you can show. It's number 3.
Especially if you have project proposal on the same day.
Life is not easy.
Yeah.
Хорошо, но только 4-й, 5-й.
I would like to walk in situation of problem 8.3 and firstly let us consider the case of SO5C and simple roots. The simple roots and I write matrices that correspond to them. in empty cells there are zeros.
So one is on third position or on the second? Like, can you the last row? What is?
I think it's 2 to 1.
2 to 1, yeah.
Yes.
The sizes of block.
It's the basis in this. Oh,
So 5.
And E2.
Isn't SO5 should be semi-symmetric?
Skew-symmetric?
Skew-symmetric, yes.
It is.
Of course, so why it's not skew-symmetric? This matrices. Yeah, so you not writing SO5?
I write SO5.
But in another
but
form where
in problem
where the
Yes,
Cartan
okay.
topology is there.
Yes, I wanted to do it, but I just, well.
and then it is easy to check. For example, I would like to note that they are different, quite different, because we have in E1 here non-trivial part and in E2 here. And then it is easy to see that
So E1 and E2, they correspond to which weights? Here?
it is E1 and it is E2.
And what about F1? Oh, it's just.
But it
So F1 is this one?
F1 is minus.
yes, it is F1 and it is F2. And it is easy to see that just looking at these two matrices.
This is bracket, yeah.
No, it is simply multiplying matrices.
Okay.
And it follows from this that, and similarly we can show that the commutator of these two matrices is also 0, and non-trivial part is checking that the Cartan matrix is such. And the non-trivial part is checking that
I don't think it's symmetric. -1 somewhere.
oh, okay.
Yeah.
Here,
Depends on,
here.
Depends on the order, yeah, I guess.
so your longer route is the first, second one.
Yeah, the second is longer.
What does it mean? It means that n
Here we have
and
3.
one.
2 isn't enough, so we have 1,
n to 1 should
1, 2. Here we should
here have -1 and
negative 2 and here negative 1. Because what if I write 2 here, it won't be 0.
Ah.
So we need 3 here.
So okay.
And
Подогнали.
firstly, I would like to write this. It is
This diagram, where is the simple roots? It's the usual one. So why E1 is equal to the simple roots? Isn't it should be?
Because it's not a sum of 2
Oh,
others.
yeah.
So if you just this is sum of
Yeah,
this 2, this
yeah,
is sum of this, and then you don't get choice.
Everything else is good.
And and it is easy to see that this matrix commutates with E1. So we have proved this. And now I would like to prove this. But
You also can check that each time you get the corresponding root vector. So you take this one, which is E2, right? Then you commute with the one, you get this one. And this one is also well,
yes,
you can find what it is.
yes, it is.
Yes, this one. And then the second is this one. You can check if this corresponds to this root. And then if I go further, it's just zero.
And it is easy to see that this matrix commutates with E2. So it is 0. And for F it is similar because this is such, and so I can transpose these equalities and get Serre's identities for Fs.
Okay.
And the second part.
Do we need G2? Do we want
It is
it
quick.
It is easier.
Yes.
Okay. Yeah.
Simple roots.
It is actually.
Simple roots are on.
It will actually scare me away from this.
So you have standard basis in C3, right? These are roots. And you have SL3. And you have like 3 roots there. And you, yes, we already. So your G2, sorry, is like that. So these are long, and these are short ones. And I think I wrote it not in good scale. So this should be 3 that comes in so this triple H means that I act by this 3 times. Then on the 4th one I get 0.
And I only write the result here. So it is.
What do you mean by action on this picture? Like,
Right. So there's this one root that corresponds to this one. I don't remember. I think it was so this one was epsilon 1 minus epsilon 2, and this one was epsilon 2 something. Where epsilon is acts on Cartan just in usual way. Cartan is a diagonal matrix 3 by 3. So epsilon 1 gives me first entry. Epsilon 2 second, and epsilon 3 third. So this is just roots of SL3. And these are roots corresponding to V and V star. And the picture that we had is this is epsilon 1, this is epsilon negative epsilon 3. And this is epsilon 2 minus epsilon 3. And so therefore this root is E1, 2. This one is V, well, you have standard bases in V3, right? So E1, then here E3 star, I think, or something. Yes, and here, and this one is E. So you just commute E12 with this one, which is just the second standard, the second element of the standard basis. So it means that I just take, well, act on this by this. I get E1. So just take this matrix 0, 1, 0, 0, right? And sorry, I have 3 by 3, right? So 0, 1, 0, 0, 0, 0, 0, 0, 0, right? And act on this. So I will get this. So this is the commutator.
And here we have such, so, and I write this, the same thing. So it is clear that E1 and F2 commute because if I apply E23 to U2, I get 0, of course, because here is 3. And similarly for F1 and E2. And now I would like to check Sears relations.
So this just comes from the definition of the G2, right?
Yes.
Yes, commutation relations, yes. You just need to look at them.
Yeah, like the problem is I didn't pay enough attention to the task when it was so trouble now.
Same.
And it is easy to see that this commutes with E23. So at it is 0. And Cartan's matrix
So this
is
0, I commute this one and add. Yes, I add what? From the picture, I would like to see this. So I have add E. So I commute E1 with E2.
Yeah. Suppose you epsilon 1. Add epsilon 1.
Yeah, so this E's are not the same. They compare.
okay.
This is a standard basis.
That's
Very bad, yes. So maybe not let not.
Oh, you just need to, I think, change E1 to 1.
No, the point is
Yeah.
that
it's E1 and it is E2.
so the thing is that when you compute E1 and E2, apply. So you take E2 and apply and get to E3
Yeah.
and then 0.
Okay.
The other way around, you take E1 and apply it 3 times and get to 0. I'm get used to the other picture where I take this. So this is like some other choice of quantization.
Just a reflection.
Yeah. It's not so bad. If two problems is a full points and the other 3 is bonus, then I think it's not so bad.
So we
You just got used to maybe
Yeah,
problems.
yeah,
Yeah.
I spoiled it.
Yeah.
after writing 4 commutators we get this. And for F-sit it is the same because we can
It's just
transpose.
converse.
Yes.
Okay. Let's
что придумал, он может не работать.
Ну, это прекрасно. Ну, в смысле, не то, что может не работать, а что-то выдумать.
А можно вот такой вопрос? Решение заключается в том, что я просто думаю, что если это диаграмма, значит у нее картановая матрица это подматрица. И как только мы отображаем, у нас все как бы relations между, ну, все соотношения между друг другом, они как бы сохраняются.
Да.
То есть там добавляются какие-то новые, но они как бы не между этими.
Ну вот они могут быть в теории между этими.
В теории, да, не совсем понятно.
Окей,
То есть может там что-то какой-то многочлен там и как-то сократиться, что в итоге это упадет в главу.
This was indeed an issue.
Так.
Тогда у меня нет решения. Проблема тоже.
Ну вот я сейчас попытаюсь это исправить. Хотя не гарантирую, что это получится. How do you think? Okay. We have a subdiagram D1 in D2. This induces the embedding of sets of simple roots. And the Cartan matrix of this set of simple roots is the submatrix of this set. And this induces the embedding of some sets EI1, FI1, HI1 in the bigger set EI2, FI2, HI2. And then we apply the functor of free Lie algebra.
E1 and E2, they're the same. Just you have more indices.
Yes, here we have more indices. So we have a free Lie algebra of EI1, FI1, HI1, which is F1. We have free Lie of EI2, FI2, HI2. This is an embedding. This is F2. Here we have the ideal of relations, and the quotient is G of D1. Here we have the ideal of relations I2, and the quotient is G of D2. And we have an embedding of relations, and hence we obtain this map. And by construction, this map is a map of Lie algebras. And the only question, and it is the hardest question, why this map is injective? Hmm? Why this map is injective? I think it's more or less obvious. Okay, I have categorical argument that we have the functor of free Lie algebras, and this is the left adjoint, so it preserves limits, so it preserves embeddings. Yes, it's left adjoint to forgetful functor from Lie algebras to sets. So, but it is clear from construction. Here we have some commutators of these letters and no relations. And here we have commutators of more letters and no relations.
Maybe we have Jacobi identity, right? Maybe that's what's bothering. Maybe some Jacobi identity. But Jacobi identity.
Well, if the concept of free algebra is okay, then I think it's okay to just say that resolve
The concept is okay, but how to see that?
Okay, I can repeat my categorical argument.
Why embedding is represented by some limits? So you say it preserves limits, okay? Why is then it's preserve embedding?
But wait.
Yes.
Is it a billion?
What is a billion?
Is this a category?
Lie algebras.
Category of Lie algebras is definitely not a billion.
Then what's the argument for the kernel?
Kernel is we have a zero map. If we have
So you just take an equalizer of zero map like this?
yes, and this is precisely the kernel. And then we can apply functor and obtain that this equalizer is zero. So, okay, I think it's not the hardest point.
Yes.
But this is point that I am. So that this map is embedding, I'm pretty sure. Okay, we know that this map is a semi-simple algebra. With the which map? If we have just okay, we have the diagonal map, which is composition this and this, and this ideal. If we go if it goes here, here, and here, we have zero, because if this ideal goes here, here, and here, it's the same. The map this, and this is zero. So yes, so this composition is zero, and this is a co-kernel, so we have this map.
Okay, you have short exact sequences, and yeah, okay, the map of the kernel is just induced.
Yes, but okay.
I'm sorry, I'm lost. Did you prove that it's injective?
No,
No, we just have this map.
Okay. So this I kind of believe. Yes.
Yes, this is.
I just want to know when you will trick me. My creativity.
No.
Отлично, particle point.
Wait, are you going to use Sears theorem?
It's okay.
Okay, I
You
use.
already used it, right?
Yes, I said this is a semi-simple algebra with the root system, and it has these generators.
No, but this is just by definition, no?
No, the fact that it is semi-simple with this root system. I don't know.
Okay, we used it for the diagonal.
We didn't use it yet, but it was said. I don't know.
Yes. Okay, almost.
I lost.
No, now we can. Wait, left adjoins preserves.
Yeah, that's true.
Wait. So you say that it preserves. No, left adjoint. Okay, it preserves co-limits because tensor product is right exact.
Yeah.
Okay, but still it is an embedding.
Well, it's still the question with Jacobi and why is it everything is right?
Yeah, you need to check that you kind of don't cancel like additional by just Jacobi identity. Don't cancel like additional variables that appear.
Well, that's kind of the same.
In blue blood
terminology.
terminology, huh?
I think it's kind of the same issue that we would have like in the map from GD1 to GD2.
But okay, so if we
Yes.
know that it is embedding, then what is the argument then?
So my idea was that now we have almost explicit description of these relations. So this is relations that are just 0 elements in this algebra. And
Oh, it's a kernel, right? It's the kernel of this map.
yes, yes,
Okay.
This is just by construction.
Yeah, but
yes.
what he said right now is the same, right? 0 elements. What is a 0 element if not something? Well,
I don't understand your question.
yeah, yeah.
But I think I just said nothing.
Yeah, that was my point.
Yes. But
So it's not a question, it's comment.
okay.
So I might,
Okay,
I may share my idea, but
okay, I think my argument. I forgot just my argument. Maybe there was no real argument. I can delete my.
no, it's
Oh, you will remember.
Probably deleted in classroom.
so my idea is that if you have this, then you have one root system is inside another,
Yes.
right? So therefore, if I take just G, which one is bigger, R2, and consider its root decomposition. H plus sum over alpha and R2, right?
G alpha.
G alpha. But then inside here I can consider, so inside, so this one is span H alpha says alpha in pi 1, right? But inside, I don't know, H1 maybe, right? Inside here, I have span of H alphas as alpha in pi, sorry, pi 2
Yeah,
here.
there's right.
And let us call it H. So I claim that H2 plus sum over alpha in R1 G alpha is a subalgebra here. That's it. This is subalgebra with the root system R1. So by Serre's theorem, we know that it's isomorphic to GR1. So we're done.
Right, so we just used the fact that one is a subroot system of another, right?
Yes.
And from that we just got the root decomposition.
Then I consider root decomposition, but I can consider here some subspaces that come from embedding of root systems. And this subspace, just because this is then root decomposition for GR1. Since this is like a closed root system, as it is R1, then this subspace is a subalgebra.
Why? Why?
Well, you just can check all the elements here, so you just check how this commutes with this, how this commutes with itself.
No. Assume if we have two roots in R1, which
So if I have, if I have G alpha 1, G alpha 2, so maybe this,
okay.
I have alpha 1, alpha 2 in R, right?
Yeah, what
So
is...
I claim, so if I have, so this is inside G alpha 1 plus alpha 2.
So we claim if alpha 1 plus alpha 2 not the root in R1, it can be the root in R2?
Right. Because
Why so?
R1, well, because R1 is actually
Oh, they're linearly not.
so R1 is is a restriction, is intercept. So you have this. So this is span. I don't know. This is complex span, right? But if I consider linear span, this will be my Euclidean space E, right? U1 and E2, and so U1 is inside this. This is my H star R.
Yes.
Right? So I claim that actually E1, so R1 is E1 intersect R2.
Uh-huh.
Is it obvious?
Yeah, well, why is it so?
So this is not obvious. We can try to prove that, but at least from that, right? If this true,
Yeah.
then I have that if alpha 1 plus alpha 2 is a root in R2, then
Yeah,
it's root in
then
R2.
I probably have whole argument.
Yes. So let's try to see that this is true. So R1.
Sorry,
So-
what's again are we proving? Like, I'm not on the miss.
We're proving that this is subalgebra. So we're taking
So it's
two elements and try to see that it's inside here.
okay. So the problem is if we take 2 and we get something outside of it. Right?
Yes, yes. So I would like to see that this is actually a root in R1. So if alpha 1 plus alpha 2 is a root in R2, then it is where alpha 1 and alpha 2 is in R1. Then alpha 1 plus alpha 2 is a root in R1 as well.
My concern is with that G2 picture. We have this small A2 system and big A2 system. And
Where is
Well, it's just...
No, but there's no subdiagram.
no subdiagrams, right? But
Right, but you have some.
we have
Right, but I really would like to use that I have subdiagram.
Yeah,
So my E is generated by some subset pi 1. So let me.
where we use it, this subdiagram.
No, we didn't use it. I would like to
Well,
maybe
it's
use it
zero relations at least.
for that.
Well, we didn't use any cell relations, actually.
now we need to prove.
Yeah, I think...
Use this subdiagram to prove this that
Yeah.
R1 is E1.
Yeah, so
intersect-
that's my idea. So I don't know. I'm kind of. Right. So let's see. If alpha 1 plus alpha 2 is in R2,
Maybe it's somehow possible to combine these two arguments. Like the first argument that we have some homomorphism of the algebras.
but this is some root system, right?
Yeah. And I watched...
And then this root system has simple roots pi,
Yes.
pi 1, sorry.
Yeah.
Then you apply W of pi 1 and get
What if pi 1 comma, how it's pi 1 prime is larger than pi 1?
That's not true because pi 1 is so pi 1 is basis in I1, E1.
In E1, yes. What if, like, consider this. If you consider only, like, large diagram, there are two. Only large root system, it's, I suppose it's A2, yeah. If you consider A2, there's two root systems. There's two, how to say it? There's
Simple roots,
two two simple roots. And if you consider only the one, then
No, the thing here is that they're in the same space.
yeah. You should. Okay.
So here I am choosing subspace and choosing all roots there.
Yeah. Understand.
And so this then pi1 is a root system of this R1 prime.
Yeah.
But I can recover R1 from pi1. So R1 prime and R1, they actually coincide. Yes.
So like it's
Both.
because of P1 prime is equal to P1.
Yes. Well, yes. So just all simple roots of R1, right? They in E1 they are simple, of course, and they of R1 prime, and we have sufficient number of them.
Yeah.
So therefore, pi1 is W, and this is W is just simple reflection corresponding to this pi1. So it does not depend on anything bigger. And R1 is also the same thing.
So we also say that these simple reflections do not throw them off the E1.
Well, it's all.
It doesn't really matter. So this is just some general
I
text.
suppose we now work on in E1.
Yes. So now I have root system, two root systems in E1.
Yes.
So I don't care about what's happening outside. So I have root systems, I have simple roots, and I have simple reflections corresponding to these simple roots. And I know how to recover root system from pi1.
Yes. So may I ask, like, you said that if we have the one space like E1, we have
Yes.
some vector space,
Yes.
and we have two root systems. Yeah.
Yes.
That's then they have this like okay, for G2, like we have two R1 prime is A2 big and R1 no R1 is A2 big and R1 prime is G2. What's wrong? Why is this not counterexample?
Pi is not inside, pi1 is not inside pi2. That's the counterexample. So,
No, I'm saying about R1 and R1 prime. So like
R1 and R1 prime.
R1 prime is G2.
So
R1
they
is
have
A2.
different simple roots.
Yeah, but we don't say that there they have the same simple.
No, I say that they have the same simple roots.
Why is it so?
Well, just because, okay. So I take R1 prime,
Yes.
construct it like this.
Yes.
Then I'm saying, take simple roots of R2,
That's,
which is inside E1. They will be simple roots of R1 prime.
Yes.
And all simple roots of R1 prime are given like that.
Okay.
So therefore, simple roots of R1 prime is pi1. So
Well, pi1 is just.
it's a basis in E1.
Yeah.
Yeah, so we constructed E1 just choosing pi1.
Okay.
Yeah, so in this case, we don't have the same
Yeah.
simple roots.
So we like. So we still didn't use the diagrams coincide.
We used.
When?
But
by
pi1
this?
inside pi2. So that's where we used.
Okay.
Okay. We have, it's pity that we don't have number.
No.
Because then I have to do something in the lecture. I wanted to use it. Okay, so, right. So let's have 10 minutes break.
Блин, надо доделать аргумент, почему вкладываются эти.
Ну доделать, нет, интересно. Но, правда, меня эти аргументы очень запутывают.
Не, мне
Можно,
кажется,
конечно.
Я очень медленно соображаю.
не, мне кажется, когда вот эти свободные штуки, там категорийный аргумент как раз очень хороший. Например, там же знаменитое использование есть, что типа
Мне
что
нравится.
если есть множество, можно взять свободную абелеву группу над ним. Да, можно взять свободную группу большую, а потом взять от нее абелевнизацию. И оказывается, что это свободная абелева группа. Если смотреть просто на конструкцию, это вообще непонятно, почему это.
А как у нас свободная абелева группа берется?
Ну просто Z, ну вот это.
Ага.
Ну, просто всевозможные.
Есть,
Сопряжен.
да, есть свободная группа, которая большая. Там еще формально эти обратные
Ну,
присоединяются.
просто свободно просто по всем этим
Да.
коммутантам.
Ну да.
Как это называется?
Генераторы.
Коммутанты?
Тант.
Да,
Ну, групповой
Коммутант.
коммутант.
да.
Да.
То есть получается свободная такая большая группа.
Коммутаторы.
Да. Туда добавляющее соотношение, что g на g в минус 1 это единичка. Потом еще факторизуем по всем коммутаторам и получаем почему-то свободную абелевую группу. И это самый простой аргумент, видимо, категорный. Вот тут хочешь что-то такое.
Да, а вот еще раз насчет, почему группы, ну, алгебры линии образуют абелевую категорию?
Я не знаю.
Сейчас ядра есть, а что там?
Но мне кажется, тут что-то...
с фактором.
Ядра.
Какой ядра? Почему?
Да, потому что какие-то виртуальные.
Не, а почему? У нас ядро ли это всегда алгебра, ли это не идеал?
Ядро это
Какое
идеал.
ядро было бы
Вот это идеал.
если бы образ с идеалом был?
Ну, ядро это... ты прав. Ты прав.
Образ.
Да, вот в этом проблема, действительно.
Короче, факторизовать можно не по любому образу.
Да.
по любому морфизму.
Ну, да.
Ну,
Ну, там
там
вот
слишком много
типа вот кто
структур,
что-то
да,
есть. Вот
бывает.
из-за
Ну,
этого.
да.
Это не знаю.
Есть. В чем была проблема?
Каком?
Вот. Мы просто взяли, написали.
Проблема, что почему вот это вот нижнее выражение, где h2 плюс сумма по корням из R1 g альфа, почему это подалки? Мы можем взять коммутатор. Вот есть формула, что коммутант g альфа 1, g альфа 2 это g альфа 1 плюс альфа 2.
И типа
Но
эта
для того,
штука
чтобы
может
применить,
лежать-
нужно показать, что альфа 1 плюс альфа 2 лежит в R1. Ну, либо
Просто
ноль.
это примерно просто следует из того, что...
Мы показали просто, что все отражениями из P1 разносится.
Что, как мы это?
Ну вот мы показали, что R1 это E1 пересечь R2.
Сейчас, ну, E1 пересечь R2 это какая-то, очевидно, root system.
Да, и мы показали, что она ровная R1.
И понятно, что P1 не содержится в этой root system, правильно?
И более того, эта новая система, она получается отражениями из P1.
Потому что она с P1 отражением получается это просто по определению R1, мне кажется.
Да.
А еще раз почему? Любая система, содержащая P1 в E1, да, любая система в E1, содержащая P1, это
Любая
R1.
система с такими же простыми корнями.
А почему у нее именно такие простые корни? Сейчас. Ну, типа, ты берешь, я правильно понимаю, что вы берете R2, берете спан P1, да? У вас E1 это что такое? Спан P1, правильно?
Да.
И говорите, что ну вот у вас... Почему не очень понимаю, как определяется R1 еще раз? Это просто пересечение E1.
R1, она и дана изначально.
R1 звездочка.
R1
Звездочка
штрих это E1 пересечь с R2. Я так понимаю.
Ну хорошо, да. То есть
дальше
это,
показывай.
это просто... Так. Ну в смысле, ну конечно оно содержит R1. Вот это R1 штрих, оно конечно содержит R1.
Да.
Почему оно ровное R1?
И R1 штрих получается отражениями из P1. Я так помню.
Почему? Вот R1 получается
Ну,
R1.
кстати, хороший вопрос.
Я согласен, что R1 содержит, R1 штрих содержит R1. Что оно получается? Отражение. Почему не понимаю, почему оно получается отражение?
Меня больше волнует вопрос, почему это положение в свободных алгебре линий.
Я не понимаю, что там компьютер рисует равенство. Ну потому что сейчас у них уже равенство. Да, видишь, делается лишний пешки, но черных выходных. Такое не выявляется, наверное.
Сколько по времени? Что у них там контроль уже прошли, да?
Да, 45 явно 50 минут, видимо, тоже 50.
Не, ну вчера, конечно, весело. Там позавчера весело.
Позавчера, да. Как он просто в переходах партию проиграл.
Да.
Вы знаете, после первого хода у него там, после хода Ладьянов проверят, у него там было не лучше. А дальше он, когда там еще на третий ответ привел, там уже сразу его проиграл, потому что потерял пешку на цепь. Нам еще были какие-то трюки со слоном. Они тоже не проходят. Его можно пожертвовать самим. Ну, типа там ферзь выходит на h5.
Черный пожертвовать.
Да, черный жертвует слона шаг. И дают младший шаг. На первом ряду вроде вторгаются, потом вторгаются. Ну, короче, там ничего нет, там можно защититься от всех шагов.
Нет, ну в какой-то момент, если черный точно сильно.
Ну, не сильно.
Ну не сильно, хорошо лучше.
Меньше нам на пешку.
Не знаю.
Сейчас только есть.
Не, мы про позавчера.
Не, ну сейчас понятно, что владелец с двойной пешкой. Даже если эту пешку просто убрать, кажется,
Okay, so let's start. Last time we stopped at the following theorem. So we have theorem. It had two parts. One is that Cartan subalgebras exist. And part two, that any two Cartan subalgebras are conjugate. And we proved part one, and let us finish with this theorem and prove part two. So we had the following lemma, which we also proved partially. It says that let X be semi-simple regular element, then we can consider its centralizer and denote it as Hx. And it is a Cartan subalgebra. And also, the second statement is that every Cartan subalgebra is of this form. So every Cartan subalgebra is of the form Hx. So okay, we proved number 1 here, and number 2 actually follows from the problem in like the 5th problem in the seminar that we didn't solve, right? We actually so I don't know. Do we want to discuss it in lecture? How would?
Well, if you
Let's
want,
vote.
can we at least discuss it in the next seminar?
Sure. Yes. I mean the main right. So you have we defined this H regular, and this is all elements X in H such that alpha of X is not 0. Then the claim is that H regular is exactly the intersection of all regular elements and H. Yes, this is for all alpha and for all roots. Well, so the idea is the following. So maybe again, so on the computational part that we can do in the seminar is that I consider a map from G H rec that sends X or some Gx to, so this is the map to G, and it sends to add G, sends this pair to the element like this. So the computational part is to prove, so claim it is a submersion. So that let me not check that. You just need to compute the differential, and then it means that each point in the image of this map is each point in the image of this map has neighborhood in the image of this map, right? So that's what it means, right? Or it also means that at G H regular is open. That means that at G H regular intersect G regular is not empty.
Why is it open?
Because every point here, right, is a point in the image of this map. and each point in the image of this map has a neighborhood around it, which is also in the image. That follows from the fact that this map is submersion. Yes. So therefore, it means that actually, so suppose that I have something in intersection. So at G, X is inside here. So in particular, this is regular. And in particular, nullity of this thing is minimal possible.
What is AG?
Sorry, it is for some particular element of group. So in particular, nullity is the minimal possible.
So it's if.
Yes.
If you find some x, that this is lies in there.
Yes. So first of all, I claim that this is non-empty. So let's take some element from here. So this element, it is regular.
Yeah.
So by definition, nullity of this element is minimal possible.
Yeah.
But at G is an automorphism of Lie algebras. So therefore, nullity of at G is the same as nullity of at X. So nullity, this is the same as nullity of X. So therefore, X is regular, right?
Yes.
So it means that intersection of H regular and G regular is not empty. So we have found some element X in H regular and proved that it is regular. Sorry, like that. So this is one fact that I would like to use. And another fact is that for, yes?
Still didn't finish the seminar problem 5.
Yes, so I don't want to check this claim.
Yeah, okay.
Yes.
Yeah, but the problem stated that H intersect with G regular is equal to H regular.
Yes, I still didn't finish.
Yeah, okay.
Okay, so let me continue. So another claim that I would like to do is that for every H in H, the following is true, that n of H nullity is the same as dimension of, sorry, it's just usual H, an element, is the same as dimension of centralizer of H. Just by definition, generalized eigenspace of eigenvalue 0 is exactly nullity of H. So, and this is just definition of n of H, all right, that we had there. But this is, so of course, inside this you have Cartan subalgebra itself, plus something else. So we can consider root decomposition, right? And what commutes with this particular H? Everything from here plus everything from G alphas where alpha of H is 0. So plus the size of the following set alpha in R. So here's alpha in R. Such that alpha of X is 0.
Too much pluses.
Yes. Yes, like that.
Okay.
So we have this. So let me now use that. So in particular, if I take H from H regular, then using this,
Yeah, and then
this
should
is
be
0.
Alpha of H.
What?
The cardinality of set that's alpha in the air, root
Yes.
alpha of H equals 0.
Of H, yes, yes, yes. Like that. Thank you.
Okay.
So in particular using, so let me call this star. If I take H from H regular, this is 0. Right? Because that's how you define the H regular. And therefore, dimension of H is dimension of centralizer of H. So in particular, centralizer of H coincides with dimension of H. What? What? Like this, yes. Centralizer of H coincides with H. So this one is, of course, inside.
Yeah.
But if dimensions equal, then they coincide. All right. So we proved this. So let me take some H from H regular intersect G regular. Then I'm using this, and I would like to say then that dimension of H is minimal possible out of all, is the minimal possible nullity in G. So since I take H in G regular, this is minimal possible nullity. Since I take H in G regular,
No, I suppose since you
no. If H in G regular, this equals to the right-hand side. Since H is in H regular, right, we have this equals to this. So dimension of H is this. Okay. So let me move to the other word. So then I would like to say, so now let me take H from G regular intersect H. Then using star over there, I have that this alpha in R such that alpha of H equals 0. So we have no such roots. So this is 0. Right? So I take G regular, right? I'm using star and I'm using this. Star and double star. Right? So I'm taking some regular element. So therefore this is minimal possible. On the other hand, minimal possible equals dimension of H. Right? So therefore this is 0. And this means that G regular intersect H is inside H reg. So we need the other inclusion then. So let me take H from H regular now. Okay, then this becomes 0. And therefore nullity of H is dimension of H then. But since dimension of H we computed it is minimal possible, minimal. of y, nullity of y. So therefore H is regular by definition. And we are done. So therefore H is regular. And therefore H regular equals H intersect G regular. Okay, so up to this technical computation,
Yeah,
we have that.
what is why G is dense? G regular is dense.
Because it is complement to some to just one algebraic or whatever, to some algebraic set.
Very skilled.
Yes.
Sorry, what?
The Zariski open, therefore it's dense. Yes.
I thought h, like small h, is an element, right?
Sorry, the question was why G-reg is dense.
Yeah, I understand.
Yes.
Wait, I'm a bit confused about this line. Where you intersect G-reg is h.
Sorry, like this.
No, like that and that one.
Yeah, I always forget about
Everywhere where it's
tails.
intersection, there is.
You can analytically continue H every time that it has short H.
The sign in, H in, or it is as a sub.
Yes, and this one, analytic continuation, is like that. Very well. Okay, what do I want? So now we believe that that every Cartan subalgebra is of this sort. So it has a semi-simple element inside, and centralizer gives me the Cartan subalgebra. So take Cartan subalgebra. Therefore, so because you consider regular elements inside, and we know how they look like. They look like this. So therefore, we have some. So take some regular element. So X inside here is regular semi-simple. And then I claim that H is HX.
So you claim that Cartan subalgebras cannot intersect.
Cartan subalgebras cannot intersect.
That's strange.
So
Why do I claim this?
They can intersect, but only by non-regular elements. Because if we have an element in the intersection of Cartan subalgebras,
then we'll have then what we have out of that is the same Cartan subalgebra. That's a true statement. Every Cartan subalgebra contains so every semi-simple regular element is contained in unique Cartan subalgebra. Okay, so I never used this board. Okay, so the proof of the second statement of the theorem over there. I would like to. What?
We only proved lemma.
Yes, we only proved lemma. So, and this is what I wanted in seminar, but anyways, my cheating didn't happen. So. Okay, so how to prove this? Right, proof of part 2 of theorem. So I define equivalence like that on equivalence relation on G regular. So define equivalence and now you should ask me why it's on G regular. It's actually because I said that Hx is defined for semi-simple regular element, and here I take just some regular element, right? So this is because the following statement is that each regular element is actually semi-simple. So let's take X regular element, consider its decomposition, its Jordan decomposition, then consider H XS. So this, if this one is, I think we saw something like this last lecture. So if this one is regular, then therefore this one is regular. So therefore this is regular semi-simple. So therefore I can construct this. But I know that if I take an element from here, then it commutes, if I take, so I would like to see that X is actually in HXS. I claim that X, that's for sure, because X is in the centralizer of XS. And this is the same. So therefore, X is actually inside this Cartan subalgebra. So therefore, it's semi-simple. So therefore, X is semi-simple. Okay, so now this is equivalence relation on Greg. And I would like to see that so claim, again, each equivalence class is open. So this follows from the following. So some question?
Yeah, why
Jordan decomposition, yes. So I would like to prove that each equivalence class is open. This is because each, so if I take X, right, from G regular. So it's regular, and I consider Hx. Then I consider add G H X rec. So we prove that this is open. Okay, so this is open. Also, this belongs to the single equivalence class.
Why it is open? It is open only in the neighbor or root of HX rec.
No. So this one is open because it can. So this is so we had this statement. Okay, why? Because each element here contains an open neighborhood which stays inside here. This is because this is surjection. Yeah, but each element has open neighborhood that stays inside here. So if I have Cartan subalgebra, take H-reg. So I claim that this, regardless of what x I choose here, it's open. Is it clear? So this is some Cartan subalgebra. So this is open. But it's also it includes x on one hand, but also each element in here. So each element in here. No, sorry. This is not very good. Hx is adjoint to Hy. So this is my equivalence relation. So I claim that all elements in here belong to the same equivalence class. And this class coincides with the class whose representative is x. Okay, so any y from here is equivalent to x. Right? Why? Because if I take y, it's either in the same Cartan subalgebra, so the hx is adjoint to hy, of course, or it is in some different Cartan subalgebra. But how do I create this different Cartan subalgebra? By by adjoint action of group. So if I take y from here, it's also if I take y from here, then hx is adjoint to hy. So therefore, each x from here has an open neighborhood that is contained in one equivalence class. So therefore, equivalence classes are open. And then the theorem follows from the following claim. I claim that G regular is connected. So if I prove that G regular is connected, then I have, and my equivalence classes are disjoint, right? Then, of course, I can have only one equivalence class because they're open. So we have H, G regular is connected. Okay, proof of claim is like that. We have, so what should I say here? So take two elements in here. Then consider line. So consider line L, which is x plus ty. So line through these 2 points. Then, so this L does not belong, so maybe let me write it like this, does not belong to algebraic set G minus G regular. Right? This is some tautology, of course, because I have at least 2 points here that belong to G regular. So it doesn't belong to the complement. Uh-huh.
Well, this construction, like we say that NG H is regular open, and any equivalent element to X is contained in it.
Any
Y is equivalent.
Any Y which is inside here is equivalent to X. Because Y, take some Y, it is of the form like this, add G times some Z, right? So I take Z from H regular.
That means that H Z is regular.
Yes. So it means that, so I claim that this guy belongs to at G H X. So therefore, and this is HY. Because this is Y, this regular semi-simple element,
Yes.
right? This is Cartan subalgebra. All Cartan subalgebras are. So if I take an adjoint of Cartan subalgebra, it's a Cartan subalgebra. On the other hand, I can, well, this is Cartan subalgebra that contains Y, so it's HY. Yes.
Almost.
Yes, okay. Right, so I claim this, so therefore L intersect G minus G regular, it's just a finite, so complex line through some algebraic set, and they do not, it's not inside this algebraic set, so it intersects it in infinite number of points. Yes, and so therefore it means that L intersects G is connected. Intersect G rec, yes, is connected. So we just avoid these points. And so therefore therefore G rec is connected, right? For any 2 points, I can go through G rec. Okay, so that's it. Whew. Okay. Now I can, with peace in mind, go to representation theory, right? Maybe not. So okay, if some questions left, you can ask. So in any case, now we have this. If we believe in Serre's theorem, we have one-to-one correspondence between Dynkin diagrams and complex simple Lie algebras. Okay. So this last part proves surjectivity and injectivity of this map from Dynkin diagrams to semi-simple Lie algebras, which is given by Serre's theorem. Simple, yes. So if we look at unions of Dynkin diagrams, yes, then semi-simple. Okay, so now let us start discussing representations. And some part is pretty similar to what was like a slight generalization of what we saw for SLN. But we still have to discuss it just to introduce all the objects. And notions. All right. Yes. Okay, so we keep notations from that we had, right? In particular, has semi-simple Lie algebra, Cartan subalgebra, root system, all this we keep. And suppose that I have some representation of G. And for some element lambda in H star, let me define well, the weight subspace V lambda to be all elements, all vectors in V such that H. So how do I put it? So HV is equals to lambda of HV for any H from H. So if definition, if V of lambda is not equals to 0, then lambda is called a weight of V, and V of lambda is weight subspace of weight lambda. And an element in here is a weight vector of weight lambda. Okay, this is some terminology. Now let me introduce, okay, we already saw this, but now on lecture. So weight lattice. Weight lattice are all elements in H star such that, well, this thing is an integer for all alpha in well, in my root system. So this is called weight lattice. Okay, so the first proposition that we have is that any finite dimensional representation of G has weight decomposition, and weights are in weight lattice. Okay. So proposition, let V be finite dimensional. Then V is a direct sum of V lambdas as lambda runs over some set P of V, where P of V is a subset of P. So, okay, the proof is the following. Well, V is, of course, a representation of each SL2 triple. Therefore, well, if my representation and corresponding homomorphism is rho, then rho of H alpha, we know that they are diagonalizable because V is a representation of SL2 alpha. We know from representation tier of SL2 that Cartan subalgebra there is diagonalizable. Also, they commute. So rho of H alpha, rho of H beta commutes. So therefore, you can simultaneously diagonalize them, right? And therefore, you have this decomposition. So can simultaneously diagonalize well, H.
We assume that there is some fixed root decomposition of G, right?
Yes. So we kind of keep everything that we had for semi-simple algebra. Yes, we have Cartan subalgebra. We chose one, but
Here it's fixed.
what is what? Yes, for where P of V is some subset of P. So this, some subset is some subset. What's important that it is inside the weight lattice. Weight should be integral.
Where did we use SO2?
Here.
Always.
This? Diagonalizable? You don't know. Why do you know this?
Semi-simple. Semi-simple element.
Sure, it's diagonalizable is in a joint representation. I just take any representation.
Okay, there is a theorem. Okay,
It's not a hard statement, but still you need something to say something. Yeah. So you say that this is some theorem.
Yeah, there is a theorem that if we have semi-simple element, then its image in any representation is semi-simple.
Okay. Well, we didn't prove that. Yeah, but yes. Okay. So yeah, you can use that or just use representation theory of SL2. What we need now is that P of V is inside. So we have some set P of V. Now we would like to see that it is inside P. And to see that, again, we use SL2 alpha. So if I take lambda, so take lambda from P of V, then lambda of H of alpha is an SL2 alpha weight of V. But so therefore this thing is, but V is finite dimensional. So therefore these things should be integers, right? So therefore lambda of H alpha, it is exactly 2 lambda alpha over alpha alpha, and this should be integer. So therefore each lambda here is inside P. Very well. So next statement that we need is that, again, we'll use SL2 to say the following. proposition. Again, let dimension of V be finite number. Because I claim that this is a weight of V as a representation of the SL2. And we know that all weights of SL2 in finite dimensional representation should be integers. So that's why. Okay. So maybe a question is why this is a weight. Right. So it is weight in here, right? So it means what? It means that if I take, there's some vector v inside here, such that if I apply h alpha, I get lambda of h of alpha v. So this is exactly what it means, that it is weight in here. But this also means that it is SL2 weight, because this is an H element is in SL2 alpha. So therefore, this is of SL2 weight. This SL2 weights a vector. This is corresponding weight. Very well. So now, yes, I would like to show that weight subspaces are invariant with respect to action of Weil group. So then, for any element W from the Weil group, we have the following. Let me write it like this: dimension of V of lambda equals to dimension of V of lambda of W applied to lambda. Okay, so for this statement, the proof. For this statement, it's enough to take just simple reflection. W is Si. Okay. So if W is Si, then again V. I claim that V lambda is a weight subspace of SL2 alpha of some weight K, where K is just the same computation as 2 lambda alpha I over alpha I alpha I. Okay. But then V of Si lambda is then V of SL2 alpha minus K. Well, you just apply Si and check that you get negative K here. Okay, so Si.
K is equal to 2 lambda alpha I, actually. Only alpha.
Alpha I here. I would like this to match a reflection that I take.
So you take it as a SL2 alpha I
Yes,
representation?
yes, yes. Yes, thank you. So Si alpha I, Si lambda, right? This will be
Oh, there we have the same alpha, right?
yes, everywhere S alpha I. Si lambda is what? It is lambda minus 2 lambda alpha I over alpha I, right? Times times alpha I. And so then if you consider Si lambda alpha I, just plug this into here, you will have k from this minus 2k, and this is negative k. So therefore it's like that. But again, from representation theory of SL2, we know that dimension of this should be equal to dimension of this. So we are done. Very good. Next, I would like to go and generalize. So introduce now highest weight representations. Okay, so let V be a representation of G, and then let me define what are singular vectors. So V and V lambda is called singular if action of n plus on V is 0. And this is singular of weight lambda. So singular is vectors, they by definition are weight vectors. And then let me introduce representation of highest weight lambda. So V is called a representation of highest weight lambda if there exists a singular vector V of weight lambda which is generating vector. So such that V is U of G applied to V.
So this thing actually depends on the polarization, right?
Yes, yes. So we fix all that.
Then decomposition is, or that decomposition is independent of polarization, right?
Yeah.
This decomposition is independent, yes. Okay, so this is highest weight. Let me now introduce one particular example of this, which are called Fermat modules. Okay, so this you also know. So for any h from, lambda from h regular, right, we can consider U of G. Okay, so for any lambda of H regular, the module like this, M lambda, it is U of G quotient by the following. It's a left ideal generated by bunch of elements. So like this, where H here is from H. Plus U of G n plus. So like that. So why this is a module? Because so I define G module structure on here just by multiplication from the left. Okay.
How do you apply lambda to H if you take lambda from H?
Something is better written here. I know, that's okay. Yeah, so lambda H from H star. No regular elements anymore.
Yeah, I was afraid of.
Yes. No.
What do you mean by multiplication? It's a module of a universal envelope.
If it's model over G, and no, not a commutator. It's like a so G is an element in U of G. Well, any associative algebra is has a regular representation. So this is a regular representation of U of G. Yes. So that's it. Yes. So.
So lambda is a representation of U of G, right?
It is a representation of U of G and end of G. It's just the same thing. Yeah. Right. Then the module like this is called the Fermat module. It's called the Fermat module. We will need them to classify all irreducible finite dimensional representations. Okay, so this goes like in a parallel with what we saw for SLN.
Singular.
Why is it highest weight?
Yeah. Why is it highest weight?
Because you try the highest weight here is the image of 1 in U of G. So if you take 1 and apply n plus, right? Then this will be in this ideal, right?
This plus is
I take one inside U of G.
Yeah. This plus is sum of ideals.
Yes. So this is yes. All sums of elements of the sort something from U of G times yes, times an element from n plus.
Okay.
Right. So if I take 1 and apply E, some E from n plus, right? Then E times 1 is 0. So it's singular, and this is why it's weight vector. So it's killed by n plus, and it has weight lambda, because H acting by H and acting by and multiplying by lambda of H is the same. So that's what's going on. So maybe this is another thing to write. So H1 is lambda of H1, and usually this 1 it's an image of 1, right? Oh, okay. This is 1. This is usually called like V lambda. And yeah. So here I act on image. So then 1 goes to some image V lambda in M lambda, right? And actually here I act on V lambda. Right? It's just some abuse of notation. Right. So I have this. Now let me introduce some order, as we had also for SLN. Introduce order. some partial order on weights. For that, to justify this order, we need the following lemma.
Maybe a very stupid question.
Uh-huh.
How can we take a quotient by on the left ideal?
So what's the problem? So your it should be a sub-representation of U of G.
Well, it will not be algebra, but
It is a represent. Yeah, we would like this to be module, G module, U of G module.
okay,
So we can.
left.
Yes.
Right?
Yes. Yes. Now, I'm not claiming that this is algebra. Yeah. Okay, so lemma is this. Again, V is some representation, and consider SL2 triple, E alpha, F alpha, H alpha, SL2 triple. Corresponding to the root alpha. Then, if I act by E alpha on V, on the weight subspace V lambda, I will end up in weight subspace lambda plus alpha. And if I act by F alpha on weight subspace corresponding to weight lambda, I will end up in the weight subspace lambda minus alpha. So proof, I will not write it here. It's just straightforward computation using commutation relations. Just the same as we did like for SLN, for SL2 in fall semester. So proof straight forward check using commutation relations. But this motivates us to introduce the following partial order for two elements, lambda and mu, in H star. Let us write lambda is greater or equal than mu if mu equals lambda plus sum over ni alpha I for well, alpha i's are simple roots, and so for some ni which are integer and non-negative integer.
Is it okay that lambda is bigger than mu, and mu is the sum of lambda and sum?
Say it again. So lambda is bigger than mu. Something is bad. Yes, maybe we should. So if I add, I go to bigger side. So therefore I should. Yes. 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 Thanks. Very well. So lemma, another lemma is about Fermat modules. And so we said that we have some root decomposition for finite dimensional representations. So for Fermat modules, we have them as well. And actually, we have them for all highest weight modules. But for now, we just need for Fermat. And for highest weight, it's just proved in the same way. So lemma M lambda is a direct sum of weight subspaces as mu runs over over weights which are smaller or equal than lambda. The proof is just using PBW theorem. So we already introduced V lambda. So proof.
Sorry, this is a statement about what are the weights of the non-motion, right?
This is statement what are weights, and first of all that we have weight decomposition. We proved it for finite dimensional.
It's infinite in the general case, but it can be finite.
No. It's always infinite. It's just sometimes it is in generic lambda it's reducible, but for some special points which are like this p, like we will see all this. In P plus, yes, it is reducible, and then you can create some finite dimensional. Yes. Actually, it's reducible in more than P plus. It's also reducible in some other points, but the quotient will be not finite dimensional. Yeah. So, right. How to prove that? So let V lambda be highest weight vector in M lambda. So it's an image of 1, right? Then we can write M lambda is generated by U of G from V lambda, but U of G by PBW is U n minus U of H U of n plus applied to V lambda, right? And this is, so this is only non-zero if you choose 1 here. Applying any H doesn't move you from V lambda. So it's U of n minus V lambda. But again, by PPW, we have a basis, some basis here is of the form P times V lambda, where P is a monomial in F1 in elements of n minus, right? But if you apply elements of n minus, you just subtract. So this basis is a weight basis, right? So all elements we have in n minus, we have basis. So n minus is this. It is sum over alpha or negative alphas of G alpha. So it has some natural basis.
So something like F
yeah.
and
Yeah. So in elements F beta 1, F beta 2, and so on, where beta are negative roots. But when I apply such an elements, I actually reduce, I actually get some weights which are smaller than lambda. Okay. So I get a basis here, which is weight basis, so therefore I have decomposition. And on the other hand, all weights are smaller than lambda. So lemma follows. And finally, so how much time do I have?
Around 5 minutes.
2 minutes. So
Have you proved the lemma?
we did.
Okay, so and how?
Yeah, so that they're all lower, but why there's such a decomposition?
Because I have basis, which is a weight basis. So that exactly means that I have weight decomposition.
So again, we just consider
I say that my m lambda is of this form, and this thing has the following basis. It's some monomial in f betas times v lambda. Each vector of this sort is a weight vector of weight. So you apply you just subtract these betas from lambda.
because of the lemma.
Right. You just subtract these betas from lambda. And so therefore this is exactly means this.
Why don't we get out of the weight lattice?
Why don't we actually we might we are not in weight lattice here. I never said that mu's here belong to weight lattice. It can be something in between, but still I construct like a root lattice out of this. So I never said that this mu belongs to weight lattice.
Wait, so it's actually an infinite sum.
Yes, yes.
So yeah, the first equality, it's.
Are they one-dimensional?
No.
Ah, yeah.
No. The picture for SL3 is like that, if you remember. So you have one root acting, another root acting. So you have like the outer contour, and then you have, so this is your lambda. And then you have actually multiplicity 2 here. Sorry, here. And then you have multiplicity here deeper, and so on. So this is how Verma model for SL3 looks like. So no, they are not of multiplicity 1, of course. And this is multiplicity 2 because I can go like that or like that.
Yeah.
Okay.
Yeah, the first like m lambda is equal to u of j, and v lambda is from because it's image of 1. Yeah.
Yes.
Okay.
So okay, my 2 minutes are now gone. Okay, so let's stop and then continue next time.
So our last goal of this is just to understand how to describe all the reducible finite dimensional representations, right?
So last what?
I mean, our main goal is this thing.
Yeah, so we need to classify now, yeah, and this can be done in relatively easy terms.
А для полупростых они все полностью разложимы?
Да, это мы доказали, ну типа доказали, да.
Когда мы это доказали?
Честно доказали.
Ну, честно, с точностью до всяких там гомологической алгебры.
Конечномерные, правильно? Да, точно. Да,
ну, конечно, да, конечномерные, конечно.
Да, точно, доказывали.
Не конечномерная, ну, Верма модуль, например, он не разложим. Ну, вот там, где он приводим, он не разложим нифига.
Бывает неприводимый, да?
Ну да. Мы так и будем строить, мы так и будем строить конечномерные. Неприводимые конечномерные, они строятся из приводимых модулей Верма. Я должен ее поставить в точку, где он станет приводимым, и отфакторизовать по подмодулю.
Да, вот эти вот условные L лямбда, там, если лямбда у нас из доминантных интегральных весов, то будет, понятно, конечномерное неприводимое построение, а если нет, то оно будет просто, оно не будет конечномерным, короче. Поэтому есть, конечно, конечномерные неприводимые построения.
Я просто до сих пор не могу осознать факт, что для алгебраических групп у нас все неприводимые построения конечномерные. А как бы алгебра
Все неприводимые. Ну для групп, да, правда.
Да, а тут как бы алгебра Ли вроде то же самое, представления те же самые.
Но некоторые не интегрируются просто.
Ну, вот,
Нет,
да.
у нас больше, представлений у нас больше.
Они просто, видимо, полиномиальными не будут.
Не, но там, то есть они должны быть интегрируются, они только если у меня они локально, как бы, локально конечны, то есть это локально, если ту тройка действует конечно, тогда они интегрируются на группу. Вот. Так что у нас больше гораздо здесь.
А мы снова будем обрезать так, что когда мы ешки не сможем поднять, да, мы...
Ну да, мы должны где-то глубже найти сингулярный вектор, по нему обрезать. Да. Угу. До свидания. До свидания. До свидания. Да, давайте 206-ю я там вам дам. Ага.